Hello, friends. Welcome to Akulmach. Today, we uncover the ultimate cosmic mystery. Join me as I dive into the hidden world of the dark matter, the invisible force that makes up to 85% of the universe. This isn't just empty space. Dark matter's gravity is bending light, dramatically coloring our view of everything from distant galaxies to the fabric of the space time itself. Learn how scientists use the concept like gravitational lensing to map this unseen cosmic web and understand its profound effect on cosmology. Let's go. Hello and welcome, all cosmic explorers, to a journey into the deepest, most profound mysteries of our universe. Look up at the night sky and you will see a tapestry of stars, planets, and galaxies, a vibrant, colorful canvas painted across the inky blackness. For centuries, we have believed that what we see is what it is. But what if I told you that the colors, the shapes, the very fabric of the cosmic masterpiece are being subtly yet dramatically influenced by something we just cannot see? Something that make up the vast majority of everything, yet remains entirely invisible. Today, we are diving into the hidden world of the dark matter, an enigmatic force that isn't just lurking in the shadows, it is the actively coloring our view of the entire universe. It is bending light, distorting images, shaping the destiny of the galaxies, all without ever revealing itself directly. Get ready to uncover the universe's hidden canvas. For a long time, astronomers thought they had pretty good handle on the universe. We observe stars, gas, dust, planets, all made of what we call a baryonic matter, the stuff that interacts with light, the stuff we can touch and feel, but our observational tools become more sophisticated, particularly in the earlier 20th century. Strange anomalies begin to appear. One of the most compelling pieces of evidence come from the observing the rotation of the galaxies. Imagine spinning a dinner plate a part closer to the center spin faster than the part of the edge, right? That is how the gravity usually work. But when astronomers like Vera Rubin studied the spiral galaxies, they found something astonishing. Stars and gas clouds on the outer edges of the galaxy were orbiting just as fast, as nearly as fast as they're closer to the center. That means the entire galaxy is moving at one speed. This shouldn't happen. If the visible matter was all there was, the outer star should be flung off into the space or at least slow down considerably. The only way for them to hold together and rotate so uniformly was if there was far more gravitational pull, than could be accounted for by the visible stars and gas, and many times more, much more. This missing gravitational pull led to a revolutionary and initially quite controversial hypothesis. There must be an enormous amount of unseen, undetectable matter holding these galaxies together. They called it dark matter. Not dark because it's a sinister, but dark because it doesn't emit, reflect, or absorb light or any other form of electromagnetic radiation. It's essentially invisible to our telescopes. Think of it like this: you see a group of dancers moving perfectly in sync, but you can only see their costumes, not the intricate rigging holding them together and moving them precisely. Dark matter is that rigging, an invisible scaffolding providing the extra gravitational glue. The current estimate suggests that the baryonic matter, everything we can see, makes up only to about 5% of the universe. Dark matter, on the other hand, accounts for roughly 27%. Remaining 68% is an even more mysterious force called dark energy. But that is a story for another time. Today, our focus is on the colossal 27% the silent architect of the cosmic structure. So, dark matter doesn't interact with light and it doesn't interact with normal matter in any way other than through gravity. This unique property means it doesn't clump up like gas or stars. Instead, it forms vast, structures throughout the universe, which we call the cosmic web. Imagine an enormous three-dimensional spider web stretching across the cosmos. This web is primarily made of dark matter. Where the strands of this web intersect, the gravitational pull is the strongest. These are the regions where visible matter, gas and dust gets drawn into the center and accumulates. And what does these accumulation of visible matter form? Galaxies and clusters of galaxies. Without the dark matter, the early universe wouldn't have had the gravitational seeds necessary to pull together enough ordinary matter to form stars and galaxies as quickly and efficiently as they did. The universe would be much emptier, more diffuse, and far less interesting place. Dark matter is the hidden canvas into which all the visible wonders are painted on. If the dark matter is invisible, how do we know it's there? Beyond just rotational curves. This is where one of the most incredible phenomena in astrophysics comes into play, which is known as the gravitational lensing. Einstein's theory of general relativity predicts that the massive objects, anything with significant gravity, will warp the fabric of space-time around them. And since light travel alongside the space-time, if space-time is warped, light's path will also be bent. It's like looking through a funhouse mirror, but the mirror is gravity itself. When a massive object like galaxy or a cluster of galaxies, sit between us and more distant background objects, its immense gravity can bend the light from that background object. The effect can magnify, distort, or even create multiple images of the distant source. These distortions aren't caused by the visible stars of the foreground galaxy alone. They are caused by the total mass, and the vast majority of that total mass is dark matter. Gravitational lensing isn't just a theoretical curiosity, it's a powerful observational tool. When we see the light from a distant galaxy stretched into a luminous arc or appearing as several distinct images around the foreground cluster, we are witnessing dark matter in action. The shape and intensity of these arcs are create multiple images, and it tells us about the distribution of the mass, and therefore dark matter in the foreground lens is known as gravitational lensing. Imagine a giant invisible magnifying glass in space. This magnifying glass isn't made of glass, it's made of gravity, powered by the dark matter. And by carefully mapping these distortions, scientists can reconstruct the lens itself, revealing the invisible concentration of the dark matter that are bending light. This is the literally how dark matter colors our view, not by adding pigment, but by dramatically altering the path of the light and different electromagnetic waves, changing the apparent shapes, sizes, and position of everything behind it. It's like looking at a painting through a rippled pan of glass. The fundamental colors are there, but their presentation is entirely dictated by the invisible medium. The gravitational lensing comes in two main flavors: strong lensing, which creates these dramatic arcs and multiple images, and the weak lensing. While less visually dramatic, weak lensing is arguably even more powerful for mapping the broader distortion distribution of the dark matter. Weak lensing occurs when the gravitational effects of the foreground dark matter is subtle. It doesn't create obvious arcs, but it imparts a tiny, almost undistinguishable shear or stretch to the shape of millions of distant background galaxies. These galaxies are randomly oriented, but if they pass behind a large sum of dark matter, their light will be uniformly and slightly stretched in a particular direction. By statistically analyzing the shape and orientation of millions upon millions of these distant galaxies across vast patches of the sky, astronomers can build detailed maps of the invisible dark matter and its concentration. These maps reveal the cosmic web in unprecedented details, showing us exactly where the dark matter is, and it is densest in that location and more diffuse in some other location. This is how we literally see the skeleton of the universe, the invisible framework upon which everything else is built. One of the most compelling visual pieces of the evidence for dark matter comes from observing galaxy cluster collisions, particularly and even known as the bullet cluster. When two galaxy clusters smash into each other, their visible components behave differently. The hot, ordinary gas within the cluster, which makes up most of their visible mass, interacts electromagnetically. It slams into the gas from other cluster, slows down due to friction and get heated, growing brightly in X-rays. But the dark matter component is a question mark. It doesn't interact electromagnetically. It just sails right through the other dark matter, like ghosts passing through each other, largely unaffected by the collision. When astronomers observed the bullet cluster, they saw exactly this separation. The X-ray glowing gas was certainly located and it was centrally positioned, slowed down by the collision. But the gravitational lensing analysis, which traces the total mass, showed that the bulk of the mass, which is comprised of dark matter, had passed through and moved ahead of the gas, and it was like watching a car crash where the visible bodywork crumpled at the impact site, but the invisible engine somehow flew straight through and ended up on the other side. This stunning observation provided direct visual proof that the dark matter is real and behaves precisely as theorized. We know it shapes the universe. We can map its distribution through its gravitational effects, but the million-dollar question remains: what is it? This is one of the most active and exciting frontiers in the modern physics. Scientists have proposed numerous candidates for the dark matter particles, and they call them WIMP, for example, as one of them. WIMP stands for weakly interacting massive particle. Then there are Axion, which are much lighter and hypothetical particles that could be produced in the cores of the star or early universe. Then there are sterile neutrinos, a heavier non-interacting cousin of a familiar neutrinos, and more exotic theories. Despite decades of search, we haven't directly detected a dark matter particle yet. It remains one of the greatest puzzles of science, but every non-detection helps narrow down the possibility, guiding us closer to the truth. Our quest to understand dark matter is far from over. Future generations of telescopes like the James Webb Space Telescopes are peering deeper into the early universe, observing galaxies formation when the dark matter's influence was even more dominant. The upcoming Euclid mission will specialize in mapping the cosmic web through weak gravitational lensing across vast areas of the sky. And on Earth, particle physics experiments continued their relentless hunt for direct detection, hoping to one day we will be able to capture the elusive dark matter particle in our laboratory. Each new piece of data, each new observation is like peeling back another layer of the universe hidden canvas. It's helping us not only to understand what dark matter is, but also how it has shaped the cosmos from the Big Bang to the present day. It is redefining our understanding of the cosmic evolution, galaxy formation, and even the ultimate fate of the universe. So, the next time you look up at the night sky, remember that there are far more to it than meets the eye. The dazzling nebulae, the majestic spiral arms of the galaxy, the shimmering clusters, they are all illuminated by visible light, but their structure, their very existence, and even their apparent colors from our distant perspective are profoundly influenced by an invisible hand. Dark matter is the silent sculptor, the unseen architect, the hidden canvas upon which the universe paints its magnificent masterpieces. It challenges our perception, pushes the boundary of our knowledge, and reminds us that the universe is far more complex and mysterious than we could ever imagine. It's humbling thought, isn't it? That 85% of the universe still waiting to be fully understood. Yet, its effects are undeniably present, can be observed today, and it colors everything we see. Our journey to unravel this cosmic enigma continues, promising new discoveries that will undoubtedly change our view of everything once again. Thank you for joining me on this exploration of dark matter and its incredible role in shaping our cosmic view. If you enjoyed this journey into the unknown, please like this video, subscribe to our channel for more cosmic adventures, and let me know in the comments what other mysteries of the universe you would like to explore. Until next time, keep looking up.